The 15-second clock. You've probably held your breath for a minute, maybe two if you're showing off. In space, without a suit, holding your breath is the single worst thing you could do. It'll rupture your lungs in about 3 seconds. The expanding gas inside your chest has nowhere to go. But the strangest part of vacuum exposure isn't what kills you. It's how long you'd actually survive. 15 seconds. That's your window. After that, the oxygen drains from your brain and you're unconscious. Your skin swells as moisture in your soft tissue starts to bubble, a process called ebullition. It's not your blood boiling the way movies show it. It's the water on your tongue, in your eyes, across every exposed membrane turning to vapor because there's no air pressure holding it as liquid. You wouldn't freeze instantly either. Space is a near-perfect vacuum, terrible at conducting heat. You'd swell, suffocate, and lose consciousness long before temperature became the problem. At sea level, 14.7 pounds per square inch hold your body together. On top of Everest, that drops to about 5, and climbers are barely functional. In space, that number hits 0. Every gas pocket in your body starts expanding at once. Every astronaut suit-up checklist starts to feel a lot more important after learning this. The only human survival data from near vacuum exposure is one guy in 1966 who lived to talk about it. In space, every second you're alive is borrowed time. He survived, and the first thing he told the recovery team was that the last thing he remembered was the spit boiling off his tongue. The shadow line. On Earth, the coldest and hottest places are thousands of miles apart. In space, they're separated by the width of your hand. And NASA doesn't actually worry most about the cold side. The sunlit side of the International Space Station reaches approximately 250 degrees Fahrenheit, hot enough to bake a pizza on the hull. Step into the shadow and it plummets to negative 250 degrees Fahrenheit, cold enough to freeze jet fuel solid. That's a 500-degree temperature swing, and it happens every 45 minutes as the station rotates through its orbit. The ISS circles Earth every 90 minutes, which means 16 sunrises and 16 sunsets every day. Astronaut gloves have 10 layers of thermal protection because direct sunlight would burn through a single layer glove in minutes. Spacewalk schedules have to account for which side of the station is facing the sun, turning EVA planning into the world's highest stakes weather forecast. And we're a species that complains about a 20-degree temperature drop in October. We built a permanent habitat where you experience a 500-degree swing before lunch. 500 degrees every 45 minutes. And we put a house there. Invisible bullets. A grain of sand just hit the International Space Station. Nobody heard it, nobody felt it, and it punched a hole through 2 layers of aluminum shielding. The math behind why is the most terrifying equation in orbital mechanics. Micrometeorites travel at 10 to 45 miles per second. Kinetic energy scales with velocity squared, so doubling the speed quadruples the destructive force. A grain of sand at highway speed would sting. A grain of sand at bullet speed would break skin. A grain of sand at orbital speed, 40,000 miles per hour, carries the energy of a bowling ball thrown at 60 miles per hour. Space isn't empty. Low Earth orbit is a shooting gallery of natural micrometeoroids and human-made debris. In 1983, a fleck of paint at orbital velocity hit a space shuttle window and gouged a crater visible to the naked eye. The ISS uses Whipple shields, sacrificial bumper layers that don't stop incoming particles, they explode them. That's the defense strategy for the most expensive object ever built. Hope the first wall detonates the bullet before it reaches the second wall. NASA tracks over 27,000 objects larger than 4 inches, but micrometeorites are too small to track. So every astronaut technically owes their survival to the fact that nothing invisible has hit the right spot yet. Every orbit of the space station is a 40,000 mile per hour drive through an invisible shooting gallery, and the windshield is 3/8 of an inch thick. The thing about space is, it doesn't need to be dramatic to kill you. Sometimes it just needs to be fast. Losing pressure. In 1971, 3 cosmonauts completed a record-breaking 3 weeks in space. They landed on schedule. Recovery crews found them still strapped in their seats, perfectly still, with dark blue patches on their faces. A single valve, smaller than a quarter, had opened during re-entry. The Soyuz 11 capsule depressurized in approximately 30 seconds at 68 miles altitude. Georgy Dobrovolsky, Vladislav Volkov, and Viktor Petsayev are the only humans to have died in space above the Kármán line. Rapid decompression causes gas embolism, air bubbles in your blood, lung barotrauma, and loss of consciousness within seconds. Opening a car window at highway speed creates about a 1 psi pressure difference. A cabin breach at altitude in a commercial jet drops pressure enough to give you seconds of useful consciousness. In space, the full 14.7 psi disappears, total vacuum, and every seal, valve, and joint is the only thing between you and 30 seconds of awareness. Explosive decompression is extremely rare. Real decompression events are usually slow leaks through tiny openings that give crews minutes to respond. Soyuz 11 was lethal because the crew didn't know it was happening and couldn't reach the valve. After 2018, astronauts learned that mysterious hole in the spacecraft was an actual item on the troubleshooting checklist. Since 1971, every cosmonaut and astronaut suits up for launch and landing. They take those suits off for the 6 months they spend floating inside a tin can. Make that make sense. The solar kill shot. In August 1972, between Apollo 16 and Apollo 17, the Sun fired off one of the largest solar particle events ever recorded. If astronauts had been on the lunar surface that day, they would have received a fatal radiation dose within hours. The margin between Apollo 16's return and that event was 4 months. Apollo 17 launched 4 months later. And sometimes the Sun decides to collect on that borrowed time, all at once. Solar particle events accelerate protons to 70% the speed of light. A chest X-ray delivers about 0.02 rem. The annual safe limit for radiation workers is 5 rem. That 1972 event would have delivered 400 rem in a few hours, the equivalent of 20,000 chest X-rays concentrated into a single afternoon. 300 rem is lethal. On the moon, there's no magnetosphere and essentially no atmosphere. Zero protection. Warning time can be as little as 15 minutes for the fastest particles. Solar flares and solar particle events aren't the same thing, by the way. Flares are bursts of light and radiation. Particle events are streams of actual matter, protons and ions, ejected from the Sun at near light speed. It's the particles, not the light, that would kill you. The entire Apollo program dodged a radiation burst that was literally traveling at 70% the speed of light during the one window when nobody was up there. 12 humans walked on the moon with the radiation shielding of a car door. Every single one of them came home. That's not engineering, that's luck. If you're learning stuff you didn't expect to learn today, I'd appreciate it if you hit subscribe. I put out content like this regularly, and it means a lot. Thanks. The human crush. Every hazard so far has come from outside the spacecraft. This one comes from inside, specifically from the chair you're strapped into. And the force that nearly killed one cosmonaut wasn't from a malfunction. It was the rescue plan working exactly as designed. Normal launch subjects astronauts to 3 to 4 Gs sustained for several minutes, 3 to 4 times your body weight pressing on your chest. A roller coaster peaks at about 3 to 4 Gs for a few seconds. A fighter pilot pulling 9 Gs in a turn needs a pressurized suit and special breathing techniques to stay conscious. During ballistic re-entry, astronauts experience 8+ Gs for multiple minutes. No G-suit, no training maneuver, just hold on. At sustained 4 Gs, vision starts to grey out. At 6, most untrained people lose consciousness. At 9 to 12, sustained for more than a few seconds, organs can shift and blood vessels can rupture. In 2008, the Soyuz TMA-11 crew experienced approximately 8 Gs during an emergency ballistic re-entry, and one crew member briefly lost consciousness. The emergency re-entry mode, the Plan B, subjects astronauts to nearly 3 times the force of the normal version, which raises the question of who designed Plan B. That same crew reported the capsule spun during ballistic re-entry, meaning they experienced 8 Gs while tumbling, basically the world's worst amusement park ride at 200 miles altitude. Plan B is 8 Gs in a spinning capsule. If you're wondering what Plan C is, there isn't one. Invisible flames. On Earth, you can see a fire. You can hear it. You can smell the smoke. In microgravity, a fire can burn in a perfect invisible sphere, with no smoke trail and no flickering light, and you won't know it's there until it's eating through the wall. NASA discovered this by accident, and the experiment that proved it almost caused the exact disaster it was studying. In microgravity, flames form spheres because hot gas doesn't rise. There's no convection to give fire its familiar shape. Some microgravity flames are completely invisible to the naked eye, burning so cool that they emit no visible light. NASA's FLEX experiments discovered cool flames, combustion that continues below visible temperatures, undetectable by cameras. A house fire gives you roughly 3 minutes to evacuate. An airplane cabin fire gives you about 90 seconds. A fire on a spacecraft gives you the volume of a school bus, no exits, and an oxygen-enriched atmosphere that turns every surface into potential fuel. NASA's experiment to study how fire behaves in microgravity accidentally created a fire that behaved in a way nobody predicted, proving the exact point of the experiment in the most stressful way possible. In 1997, a lithium perchlorate canister malfunctioned on Mir and produced a blowtorch-like flame that burned for 14 minutes. The crew couldn't retreat because the fire blocked one of 2 escape capsules. They fought it wearing gas masks with limited oxygen while traveling at 17,000 miles per hour. Your next fire drill at work should feel a lot more manageable. 14 minutes, 1 blowtorch, 2 exits, 1 of them on fire. And the nearest fire department is 250 miles straight down. Poison air. You can patch a hole, you can dodge debris, but you can't hold your breath for 6 months. This hazard is already inside with you, circulating through the same air vents you're breathing from right now. The ISS has evacuated entire modules more than once, and the reason wasn't a hull breach. In January 2015, crew sealed hatches and retreated to the Russian segment when sensors flagged ammonia contamination. Ammonia runs through the station's cooling system, and it's lethal at low concentrations. You'd notice a gas leak in your kitchen within minutes from the added smell. Carbon monoxide in a house can kill you overnight without you ever waking up. On the ISS, a single ammonia line crack would make the air lethal within minutes in the affected module, and ammonia has no color. Without the CO2 scrubbers running, carbon dioxide levels become dangerous within hours. Symptoms start with headaches and confusion, then progress to unconsciousness. During Apollo 13, CO2 scrubber failure nearly killed the crew before engineers on the ground duct taped a sock, a flight manual cover, and a plastic bag into a makeshift adapter. The air on the ISS isn't clean either. It's a constantly monitored mixture that includes trace amounts of formaldehyde and benzene from off-gassing materials. The station has a device that does nothing but sniff the air for over 20 different ways it might kill you, and astronauts have learned to not think too hard about what that implies. That Apollo 13 fix is either the greatest engineering feat in history or the most terrifying. The air keeping you alive on a spacecraft is 1 cracked ammonia line away from being the thing that kills you, and you'd never smell it coming. And we haven't even talked about what happens when you try to come home. The Cosmic Junkyard. There are over 130 million pieces of debris orbiting Earth right now. Most of them are smaller than a marble. All of them are moving fast enough to punch through steel. And the scariest part isn't the debris we've already created. It's what happens when 2 pieces collide. In 2009, Iridium-33 and Cosmos 2251 collided at 26,000 miles per hour, creating over 2,000 trackable fragments, each one now a new bullet. That's Kessler syndrome, a chain reaction where collisions create debris that causes more collisions, potentially making entire orbital bands unusable. A hand grenade produces fragments moving at about 2,000 feet per second. A high-powered rifle bullet travels at about 3,000 feet per second. Orbital debris travels at 25,000 feet per second, roughly 8 times faster than a rifle bullet, with every fragment carrying the energy of a small bomb. The ISS performs debris avoidance maneuvers multiple times per year, dodging objects they can actually see coming. We can't clean up space debris with any current technology at scale. Every proposed solution, lasers, nets, harpoons, works on a handful of objects. There are 130 million pieces. One of NASA's proposed cleanup strategies is literally a giant net, the same technology fishermen have been using for 10,000 years, adapted for objects moving at 17,000 miles per hour. 60 years of human spaceflight, and we're still just borrowing seconds from a universe that hasn't noticed us yet. We spent 60 years reaching for space and built a cage of shrapnel around the planet on our way up. The Plasma Cocoon. For about 4 minutes during every return to Earth, astronauts are surrounded by superheated plasma. Mission control can't reach them. They can't reach mission control. They're falling at 17,000 miles per hour, completely alone. Those 4 minutes have a name. Astronauts call it the blackout, and during Columbia, it never ended. Re-entry plasma temperatures reach approximately 3,000 degrees Fahrenheit on the heat shield surface. A blast furnace for smelting steel runs at about 2,300 degrees. The surface of the sun is about 10,000 degrees. Re-entry plasma hits 3,000 degrees and higher, hot enough that the air itself becomes electrically charged and glows. Communications blackout lasts 3 to 4 minutes as ionized gas blocks all radio signals. Heat shields ablate by design, sacrificing material to carry heat away from the capsule. Re-entry heat isn't caused by friction, by the way. It's caused by compression. The spacecraft plows into the atmosphere so fast that air molecules can't move out of the way, compressing and superheating into plasma. Same physics that heats a bicycle pump. The heat shield strategy is fundamentally let the outside of the spacecraft slowly burn away so the inside doesn't. And everyone agreed this was the best plan we've got. For 4 minutes, you're inside a fireball, deaf to the world, watching the windows glow orange, hearing the heat shield crackle, and the only thing between you and 3,000 degrees is a shield that's designed to disappear. The DNA shredder. Every second you're outside Earth's magnetosphere, a particle from an exploded star is passing through your body. Not around it, through it. And every single one leaves a trail of destroyed DNA behind. We have no technology that can stop them, and a Mars crew would be exposed for 3 years. Galactic cosmic rays are atomic nuclei, often iron, accelerated to near light speed by supernovae. A single heavy ion can destroy every cell along its path through tissue, a straight line of dead or mutated cells cutting through you like a microscopic cannonball. A dental X-ray sends photons through you, and they pass through without much interaction. A cancer radiation beam targets a specific tumor with focused energy. A single galactic cosmic ray ion shreds 100,000 cells in a line, and you'll never feel it. Earth's magnetosphere blocks most of them. The ISS gets partial protection. The Moon and Mars get nearly none. NASA's current radiation career limit means a Mars mission would use up an astronaut's entire lifetime allowance, and possibly exceed it. Thicker walls don't help either. Adding more shielding material can actually increase radiation dose, because when cosmic rays hit heavy atoms like aluminum, they produce showers of secondary particles. The shield becomes the weapon. The universe managed to design a bullet that gets more dangerous when you try to block it. Astronauts see bright flashes behind their closed eyelids in the dark. Those aren't dreams. Those are cosmic rays hitting their retinas. The universe reminding them, one flash at a time, that nothing up there is safe. The silent flash. Everything on this list can kill an astronaut. This one can kill a planet. And we only discovered them because nuclear bomb detectors pointed at space kept going off. Gamma-ray bursts are the most energetic events in the universe since the Big Bang. In 1967, Vela satellites monitoring for nuclear tests picked up massive energy signatures from deep space, classified as possible Soviet weapons. Turns out the explosions weren't coming from any country. They were coming from other galaxies. The sun converts 4 million tons of mass into energy every second. A gamma-ray burst releases more energy in 10 seconds than the sun will produce in 10 billion years, concentrated into a beam that could sterilize a planet from across the galaxy. A burst within about 6,500 light-years could strip Earth's ozone layer, exposing all surface life to lethal UV radiation. The Ordovician extinction, 445 million years ago, may have been triggered by a nearby burst, killing 85% of marine species. There's no warning and no defense. Gamma rays travel at the speed of light, so the first sign is the burst itself. They aren't rare either. We detect one per day from across the observable universe, every single day. The only reason we're still here is that they're far away and their beams are narrow. It's a cosmic lottery, and Earth has been winning for 4 billion years. The universe is firing the most powerful weapon in existence in every direction at all times, and we've just been sitting in between the bullets. And the cruelest part about a gamma-ray burst? You'd never even know your borrowed time was up. One burst, 10 seconds. More energy than the sun will ever produce. And you'd never see it coming, because it arrives at the speed of light. By the time you see the flash, it's already over. If any of this made you look at the sky a little differently, consider subscribing so you don't miss what comes next. Thanks for watching.